Hello, students. As you know, in the coming weeks, we shall be going through an online course about quantum theory. I will be posting regularly recorded sessions on VLE, which you can then follow when it's most convenient for you. We shall be going through section 8.2 from the MathSec syllabus. We will start by discussing the photoelectric effect, which will take us back around 100 years ago. There was this phenomenon which amazed physicists at the time because they could not yet explain it. It consisted in shining electromagnetic radiation, which is usually in the ultraviolet region, onto a metal surface, and in return we get electrons knocked off or emitted from the surface, but only if certain conditions are met. The facts that were observed from this experiment, which confused the scientists at that time, were, firstly, that emission did not occur for any frequency of radiation, but only above some value called the threshold frequency, which is usually denoted as F0, and which depends on the particular metal being irradiated. We define the threshold frequency as the minimum frequency that will cause emission. Another observation was that emission starts the instant the surface is exposed to radiation, meaning there is no delay. So here we are not talking about an effect that resembles heating, for instance, which requires a certain time before a particular temperature is reached. Now, what about the number of emitted electrons? We find that it is proportional to the intensity of the radiation. But the intensity had no effect on the kinetic energy, which means the speed, of the emitted electrons. In fact, strangely enough, their kinetic energy depended on the frequency of the incident radiation rather than the intensity of the radiation. All these scientific facts confused scientists because the theory of light at that time treated light as a wave, but could not explain these results. The so-called classical or wave theory of light predicted that if the light intensity increased, then so should the kinetic energy of the photoelectrons, since more energy is now reaching the metal surface. But, as we said earlier, the intensity only affected the number of ejected electrons rather than their kinetic energy. Moreover, the classical theory predicted that emission should occur for any frequency, not only for those above the threshold, given that the intensity is sufficiently strong. However, there again, this does not happen. In fact, as we said, experiments show that 1, the maximum energy of the emitted electrons is not proportional to the light intensity, and 2, electrons are not emitted for all frequencies, which contradicts, as we said, the classical or wave theory of light. This meant that the existent theory of light needed some tweaking, and this is where Einstein comes in. Let me show you this short video clip on YouTube.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also... What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Okay. So, Einstein introduced this revolutionary idea that light could behave both as a wave and as a stream of particles called photons, which consist of packets of energy. Each packet is in fact called a quantum of energy, and that's where the word quantum comes in. Each packet carries an amount of energy given by E is equal to hf, where h is a constant called Planck's constant. It is equivalent to around 6.6 times 10 to the minus 34 joule second, whereas f is the frequency of the radiation in hertz. This was in fact the key that explained the photoelectric effect. This equation relates energy to frequency. In fact, it shows that the energy of a photon, in other words, the energy of a packet of energy, is proportional to the radiation frequency. And this explains why photoelectric emission only starts above some threshold frequency. Because for the photons to be energetic enough to knock off electrons from the surface of the metal, then the frequency has to be sufficiently high. Moreover, by increasing the radiation intensity, this means that more photons are reaching the metal surface per second, thus increasing the probability that more electrons are ejected from the surface. And this explains why the number of emitted electrons increases with the radiation intensity. But how does emission exactly occur? Einstein proposed that when a photon collides with an electron, it must either be reflected with no reduction in energy, or it must give up all its energy to the electron. Moreover, the energy of a single photon cannot be shared amongst the electrons, but can only be absorbed by a single electron, which absorbs the energy of one photon. Einstein reasoned that if the energy of a photon is hf, then part of this energy must be used to overcome the forces that bind the electron to the metal surface. Now, here we are not talking about those electrons that orbit the nucleus inside atoms, but metals contain free electrons that are able to wander randomly in the metal. However, these are still bound to the metal surface. So part of the photon energy must go to break this electron free from the metal surface. The remaining energy then appears as kinetic energy of the ejected electron. And this brings us to Einstein's photoelectric equation. HF is equal to W plus half mv squared, where HF is the energy of each incident photon of frequency f. W, we call it the work function of the surface, which is defined as the minimum amount of energy necessary to release a free electron from the surface, whereas half mv squared is the maximum kinetic energy of the emitted electrons. Note that if HF is less than W, meaning that if the energy of the photon is less than the work function, then there is not sufficient energy to release an electron. Hence, it follows that if the frequency is equal to the threshold frequency, then we get HF naught is equal to W plus 0, which means that the electron is ejected with no kinetic energy. Hence, we get this equation that gives us the work function W is equal to HF naught. This is useful in calculating the threshold frequency. Of course, we can always convert from frequency to wavelength using the equation C is equal to F lambda. And so we can substitute F for lambda by using F is equal to C on lambda. So we get also the equation work function equals hc on lambda naught. And don't forget that c is the speed of electromagnetic waves in vacuum. So this brings us to the end of this online session. I hope you liked it. Bye.